All right, we're in the next portion of our lecture today, 8.4 ions, their electron configurations and sizes. So in nearly every case of bonding, the electrons are either shared or transferred in a way that gives the valence shell of each atom a noble gas configuration, or in other words, a full valence shell. So really what every atom is longing for is to have their valence shell of electrons filled. We can actually predict these formulas of ionic compounds by looking at the electrons in the valence shell. So generally when we refer to ionic compounds, we're referring to the solid state of the compound. And the solid state is such that it minimizes the negative-negative and positive-positive repulsions and maximizes the positive-negative attractions. So it looks like this. This is how ionic solids are kind of set up, where the distance between negatives is as great as possible, as well as the distance between positives being as great as possible. An example of this bonding and sharing of electrons can be seen in the compound formed by calcium and oxygen, and their valence electron shell configurations look like this. So in calcium, we've got an argon noble gas shell, which means that you have all of the electrons before this accounted for, and then it has 2 electrons in its valence shell, denoted by that 4s2. And then we have oxygen, which has a helium configuration, and then it has 6 electrons in its valence shell, 2 in the s orbital and 4 in the p orbital. And because of oxygen's electronegativity, which is 3.5, it's much greater than calcium's, and so oxygen will pull the electrons from the valence shell of calcium, and we'll actually get 2 ions. Okay, so because that difference is 2.5, it's a pretty large difference. Oxygen actually pulls those electrons totally away. And we get this transfer here with a cation of calcium and an anion of oxygen. So in predicting the formula, we simply need to look at how many of each atom we need in order to create an electrically neutral compound. And since calcium and oxygen atoms have equal but opposite charges, we'll just need 1 of each, forming the empirical formula of calcium oxide CaO. And you might remember having done this a while before, but we're going to get to look at it a little bit more now as well. We can proceed with the same principles in other cases. For example, aluminum and oxygen, where aluminum's configuration has 3 electrons in its valence shell, so it will lose those to form the aluminum 3+ cation. And we just saw oxygen will form a 2 negative anion. So in order to form the ionic compound, to have an electrically neutral charge, we'll need 3 oxygen ions for every 2 aluminum ions, forming the empirical compound Al2O3. So the -2 we're basically multiplying by 3, and the +3 we're multiplying by 2, so that we get +3, or +6 and -6, and that cancels out. So table 8.3 shows the general trend of ions created in distinct groups, and you guys know this as well. Group 1A forms a positive ion generally, except for hydrogen. Group 2A forms that 2+ charge. 3A, the only one that's really consistent is aluminum. And then group 6A and 7A are also consistent with -2 and -1 ions that are formed respectively. So now let's look at the sizes of ions, okay? The actual sizes that they are. So they determine a good deal about the properties and stabilities of ionic compounds, and we'll mostly focus just on trends here, not exact sizes. So we consider ion sizes relative to the parent atoms, okay? So we're not looking at them relative to one another, to differing atoms necessarily, but we look at them compared to the neutral atom itself, so the atom that hasn't gained any electrons or given any electrons. And since cations have a positive charge, they're actually losing electrons, meaning that the resulting ion is slightly smaller than the parent atom. Okay, so if you're losing electrons, you're gaining a positive, or your charge is becoming positive, and you're actually going to have a smaller atom. The opposite is true with negative ions. As they gain electrons, they're larger than the parent atoms, okay, without any gain or loss of electrons. But the location of the parent atom is also relevant. As we travel down groups on the periodic tables, the atoms increase in size, which makes sense because we're adding a full or a full shell basically every row that we travel down. Another trend is that the relative sizes of the isoelectronic ions, meaning ions with the same number of electrons. So we're going to examine those as well. Isoelectronic, again, meaning same number of electrons. Okay, the two factors to consider when looking at the relative sizes is the number of electrons, and we compare that with the number of protons, right? Thinking about how they are attracted to one another. So in isoelectronic ions, the number of electrons is held constant while the number of protons fluctuates. We're actually looking at different atoms, right? They just have the same number of electrons, but we're looking at different identities. So take this group with the neon electron configuration, for example. Okay, so they all have the same number of electrons as neon does. And we have oxygen that has 2 extra electrons, fluorine, which has 1 extra electron, sodium, which has lost 1 electron, magnesium has lost 2 electrons, and aluminum has lost 3 electrons. Okay, so think about that. The one with the most protons relative to the electrons will actually pull in the electrons the most tightly, right? Because of that negative positive attraction. Whereas the one with the fewest protons will be larger. Okay, so the one with the fewest protons, oxygen, will be the largest because it's attracting those electrons the least, and the one with the most protons, aluminum, will be the smallest. All right, now let's look at energy effects in binary ionic compounds. We recognize that an ionic compound, as in any bond, the attraction occurs because of the energy required to hold atoms together is less than the energy required for the atoms to be separated on their own. That's why bonds form, is because their energy required for that bond to exist is less than the energy required for them to be isolated. So lattice energy is considered the change in energy that takes place when separated gaseous ions are packed together, forming an ionic solid. So we're looking at this change that takes place for this bond to form, okay, this ionic solid. So we look at this from the system's point of view, meaning that a negative sign will indicate an exothermic process and a positive sign indicates an endothermic process, meaning that when these compounds when this compound forms, it will have a negative sign showing that it has given off energy, right? Which means it takes less energy for that solid to exist than for those two ions to exist on their own. Now, when we're looking at the total energy released, we can look at the compound forming in distinct steps. Okay, so here's an example. We're looking at total at the formation of lithium fluoride. Okay, and so individually we look at each step. Solid lithium has to become gaseous before it will actually bond with fluorine. Okay, so the process for that is it requires or gives off 161 kilojoules per mole, okay? Whereas the ionization of lithium atoms then, so they're giving off an electron, that requires 520 kilojoules per mole. And then we have the dissociation of fluorine molecules, which is 72 kilojoules per mole, and then the formation of fluorine ions, which that fluorine atom is now receiving an electron, and that's negative 328 kilojoules per mole. And the formation of this solid, so now those two ions are finally coming together, is negative 1047 kilojoules per mole. And so that, if we look at adding all of those up together, we get a very large negative number, which means that it's giving off a lot of energy, meaning that it's more likely to exist as lithium fluoride, the ionic lithium fluoride solid, than as individual lithium and individual fluorine. Here's another way we can look at that. And overall, we get that negative 617 kilojoules per mole of lithium fluoride, meaning a lot of energy has been given off. Okay, so remember, we're thinking about it in terms of the giving off of energy from this molecule itself, So negative means giving off energy. So we can see that this process is very exothermic because it releases so much energy, right? We start at this energy level up here, and we go up to break down some molecules, go up some more, we go up just a tiny bit more now that we have these ions, and then it gives off an immense amount of energy after all, overall. So another thing that we need to account for in this bonding is the shape of the compound based on ionic forces, right? These solids, they form this lattice kind of shape where we've got a positive, then a negative, and a positive, and a negative. And the positives are all separated from one another as far as they can be, and the negatives are all separated from one another as far as they can be as well. So here's another way to look at it. Without those lines separating them, but each negative fluorine is as far away from another fluorine as it can be, and each positive lithium is doing the same with other lithiums. Now, nearly all binary two-element ionic compounds formed by alkali metals and halogens have this precise structure, okay, that lattice. And when we're calculating these, we can complete them by using this equation, right? The lattice energy equals K times Q1 times Q2 over R. And K is a proportionality constant, so it'll often be given to you, or you'll be solving for it. And Q1 and Q2 are charges on ions, so that +1 or +2 or +3 or -1 or 2 or 3. And R is the shortest distance between the centers of the ions, which will also be given for you. Okay, now partial ionic character of covalent bonds. So sometimes we actually do see a little bit of ionic compound, or a little bit of ionic character between bonds. But the most important thing is that there are similar attributes between ionic bonds and polar covalent bonds, right? We need to see the different types of bonds kind of as a spectrum rather than as cut and dry different types. And basically, the biggest difference is what percentage of ionic character that they have. If they're more than 50%, they're ionic, okay? If they're less than 50% ionic in character, then they're polar covalent. So here you've got electronegativity differences and how we define them, right? So HF it has a pretty large electronegative difference, but its character that we've seen in labs through experiments is that it's less than 50% ionic in character, and so we still consider it polar covalent, not ionic. Okay, whereas lithium iodide, for example, has about 1.5 electronegativity difference between the two atoms, but it has a greater ionic character than 50%, so we consider it to be an ionic bond. Okay, so there's some gray areas here, but we look at not only the actual math between the electronegativity of the two atoms, but we look also at how they react in space or in real life so that we can make better assumptions about them, or we can label them a little bit more accurately. All right, let's look at 8.7, the covalent chemical bond. Okay, so we've gone through ionic, a little bit of polar covalent. Let's keep going with covalent. So when looking at methane, which is CH4, we see that it forms because it requires substantially less energy to exist as a molecule than to exist as an individual carbon and hydrogen atoms, right? The purpose of bonding for all these atoms is to get to a lesser energy state, right? So we think of each carbon-hydrogen interaction as individual bonds, and the total energy of the molecule can be divvied to each of the four bonds. Okay, so here we have four bonds between carbon and hydrogen. There's this bond, this bond, this bond, and this bond. Okay, so it's this pyramidal shape. Now, let's just review models for a second. In science, we can only explain how nature operates on a microscopic level based on our experience on the macroscopic level, right? So these representations that result are considered models, okay? These are not actual sizes of atoms, right? We cannot visibly see atoms, so we have to come up with representations of what we think they look like, and those things are considered models. Okay, so here are some fundamental things for models. I encourage you to write these things down, go over them, and understand them accurately. Okay, so there's this page, and then there's one on the next page. You will also have these PowerPoints, access to them as well, so that you can look at them also. So the important thing to note is that models are not always equal to reality. Okay, there are mistakes that are made in models, but it's our best representation based on what we've experienced thus far in life. So we constantly are changing models and trying to make them better, but you can actually learn a lot from a model when it's wrong, right? So if you have a poor model that's made, you actually end up learning a lot from that model.